Looking at the two model equations we gave you, we can figure out which one belongs to the prey population and which one to the predator population by considering the signs of the various constants in the information that we gave you. We told you that the prey grows at a constant rate of 0.5 per year. So since population growth is, of course, positive and depends on the population already present, we can see that this term, A, x of t, should be part of the equation dealing with the prey. Similarly, we told you that the predators die out. Similarly, we told you that the predators have a fixed lifespan of 5 years. This means that the rate of change of the predator population will have a negative component that is also directly proportional to the total population at a given time. This matches this term right here, negative c times y of t. So now that we know that x represents predator and y represents prey, let's talk about these terms that include an x times y factor. This factor of x times y represents predator times prey, and this is proportional to, basically, how often individuals of the two species meet. We know that whenever a predator meets its prey, the situation ends up being pretty advantageous for the predator, but not so great for the prey. This is shown in our equations by the fact that this interaction term in the equation for the rate of change of the predator population has a positive sign in front of it. Whenever the predator meets its prey, this population can grow. And the opposite is true for the prey population, since this interaction will lead to members of the prey dying. Determining these constants A, B, C, and D should actually remind you a bit of dealing with our SIR model problems in Unit 3. Our coefficients dealing with lifespan and growth rate correspond to the different time constants that we used for moving people and mosquitoes between infected, recovered, and susceptible populations. Now, since we've already matched A with the growth rate of the prey population, we can write down A equals 0.5 per year. In the same way, since C corresponds to loss in the predator population, we can set its value equal to 1 over the predator lifespan, or 1 over 5 years. In order to calculate B and D, the other two constants, we need to make use of the last piece of information that I gave you, that our ocean populations will reach an equilibrium situation when there are 5 times 10 to the 6 tons of prey and 1 times 10 to the 6 tons of predator. If we do some simple algebraic manipulations of the equations that I showed you above, and also plug in 0 for the rates of change of either population, showing the equilibrium situation, we can solve for B and D by simply inputting the values for A and C that we just decided upon. This results in B equaling 5 times 10 to the negative 7, 1 over year times tons, D equaling 4 times 10 to the negative 8, 1 over year times tons. When we plug all 4 of these values into base values, we can move on to the next part of the problem. In the function food chain, we implement the forward Euler method using the rates of change that we just figured out using our differential equations. Of course, we've plugged in prey in the place of x and predator in the place of y. And finally, we move on to our sensitivity analysis. To account for the lower limit of values, we make a copy of the base values dictionary and multiply each value corresponding to each key by 0.9. And we do the same thing for the upper limits by multiplying each value by 1.1. These lines down here select the most critical parameter based on which parameter has the greatest difference between its high results and its low results. However, we can also figure out the most critical parameter by just looking at the plots that we get when we run the program. Our first plot shows the amount of prey in tons versus time, and the second shows the amount of predator in tons versus time. The colors dictionary, which you may have seen toward the top of the code, paired each parameter that we're looking at with a different color. Remember, we're interested in seeing which of these parameters has the greatest impact on the maximum value of the prey. So in order to pick out the most critical parameter, we need to compare the maximum amount of prey graphed by the upper and lower curves of either series in this top graph. We can see, for example, that if we look at the yellow curves, their maximum values, here and here, are not really that far apart. If we look at every pair of curves that are the same color, we can see that this one that is cyan, or the light blue, has the greatest distance between its peaks. Looking back at our colors dictionary, we see that cyan, or C, is paired with D. Let's look at our final graph again for just a little bit more analysis. We can see that both graphs exhibit a periodic behavior. It looks almost like we have a cosine and sine function. Initially, our prey population increases, which leads to an increase in the predator population shortly afterward. This, however, leads to a decrease in the prey population, and so on and so forth, back and forth. Upon closer inspection, we can see that these are actually not perfect sine and cosine functions. In fact, the forward Euler method leads to a blow-up of periodic functions over time. We'll see a very clear example of this explosion of amplitude if we increase the end time and the step size. Let's see what our plot looks like now. This is a very interesting looking plot. We can see that in the predator population, we start with a peak-to-peak height of approximately 60,000 tons. And after 200 years have passed, we have a peak-to-peak height of approximately 150,000 tons. That's a pretty dramatic increase. If we use the symplectic Euler method instead of the forward Euler method here, we can prevent this expansion in amplitude, just as we talked about in our earlier problems involving mechanics. We can see that many methods prove useful in very different situations, whether dealing with diseases or fish populations or pendulums. Great job on Unit 4, and get excited for Unit 5. We're going to look at something totally different, how anti-lock brake systems work.